got it show.
Yes.
Oh, yes, now we are already recording. So welcome, Aarne.
Thanks. And, so some of you have seen the version of this paper. There is something new here as well, so it's not just repetition for anyone, I hope, but some of it will be. And the background here, which I try to take quite far back, and this would actually be some comments to what Stefan was saying, so I hope you join us soon. So how could AI solve mathematical problems? And there is quite a lot of hype about this. Just this weekend I got this message about the new company Math Inc. Dedicated to auto-formalization, the creation of verified super intelligence. And their claim is that if they solve math, then they solve everything. Okay, so this is a very hot topic. And as we know, so there are kind of two approaches, like in all much else of AI as well. So we have symbolic AI and we have neural AI. Used to be called statistical AI, but now I think it's very much absorbed by the neural. And theorem proving is a prime example of symbolic AI in this field, and language models the current state of the art in neural AI. And as we also know, so symbolic AI can be made reliable and have no hallucinations, whereas in neural AI you cannot escape hallucinations. But symbolic AI has restricted problem-solving capacity, one could say, whereas the neural AI can find unexpected solutions by guessing, combining stuff in unexpected ways. One way to combine this is what I also heard recently is called a federated system, where you have some problem that comes to a large language model, which then guesses a solution, which then a theorem prover accepts or rejects. And in this way, we can use kind of the good parts of both of them. So LLM is good at guessing, and the theorem prover at checking. And this was made even more prominent in this last year's Google AlphaZero success in solving mathematical Olympiad problems. So they have they generate formal problems in the syntax of the lean theorem prover, and then they let lean check them, and there is actually a reinforcement learning where their solver learns to avoid some errors. There was something quite interesting here which I turned my attention was that they needed to have a manual translation of the problems to start with, because, and I think you can easily imagine that if you have if you make even the smallest possible mistake in your conversion to a formal problem, then you can get an impossible problem, or you can get a trivial problem, but very likely you get something else than the original problem, and then this solution makes no sense. So this was done manually because there is no system that is good enough to do it automatically. There was no, and there still isn't. So this brings us to auto-formalization as a part of such a system. So automatic formalization, translation from informal to formal. And this is a kind of a hot topic due to these AI attempts. There's also symbolic auto-formalization. So you have both symbolic and neural. So of course the prime example here is these controlled languages for mathematics, such as NAPROSH and Fortel, GFLean. I would will list some others as well. And they are brittle in the sense that they only cover fragments of informal mathematics. So if you try to formalize something from a text, they most probably give you a syntax error. Then you have no neural auto-formalization, which can learn. I'm putting this into quotes because I want to avoid this anthropomorphic jargon about AI. Learn is of course a technical term as well. To auto-formalize from large amounts of data, typically they might reach 30% adequate with minor corrections. And actually one issue here is how to assess the quality in a more precise way. The problem is lack of training data, lack of these formal-informal pairs that the system could learn from. So I will come back to that. If you have followed this Mathematics Olympiad story, so this year Google's DeepSync Gemini was able to reach a gold medal level. And what is more, they didn't use formal proofs at all, but they went directly from informal statements to informal solutions. So this sounds very impressive, but I would say that this is a sidetrack if we think about the problem in its entirety, because these solutions have to be checked by humans, just like the human participants' solutions. And this is okay if you are thinking about mathematical Olympiad competitions, but if you want to have a scalable, automated AI system, so of course this will not do. But of course it's very impressive. So what we would like to have is checked informal solutions. So you have as before, so we have an LLM guessing a solution to a problem, and then the theorem prover either accepts or rejects it. And then if it is an informal solution that you want to get, then you get it in by an informalizer. Either you get the accepted solution or you get the explanation why it was rejected, but in a language that you can understand. And maybe this rings a bell. So the wider picture which I want to put this is certifying algorithms of Melhor from over 10 years back, where we have some program which is in his case, so it was something that maybe a graph algorithm which was too complicated to verify, but it was very optimized, so you got something which was good to use, but you were not quite sure whether the results were correct. And the way he wanted to then add reliability to this is that the certificate. So whenever a program produces a solution, then it also produces a certificate that can be checked by some independent checker program. And this is applicable to the situation that I showed here, namely that if you think about this situation here, so we have an informal proof from LLM. So we want to get an informal proof because we that's what we can read, and maybe that's what the reviewers can assess. But we also get the corresponding formal proof, and this we get if we have a federated system where we have a formal prover as well, and then we have a checker, the formal proof checker. We are interested in why the informal proof, but the formal proof is there to convince us that it's a correct solution, but it remains to verify that the informal proof Y really matches the formal proof W. And if we don't have this, so then, and this is actually the checker, the part of the checker program, so then we can still rely on the system. But the good news is that I think we can have this last thing as well via symbolic informalization. So the most important slide is this, where you should pay attention to the arrows. So informalization is something that we can build as a total function. So because the formal system is limited, so we can make sure that we can always produce something from it. Whereas in the opposite direction is partial. So we can't be sure that we get a good formalization from everything that is written informally. This is means that the informalization is something that we know how to do, and there is no essential need for non-symbolic or neural informalization. There's no essential need to guess. Whereas the formalization may require guessing. And then we are interested in seeing how symbolic informalization can help even here. So, and we'll cover both of these. So to me, symbolic informalization has always looked like something that is feasible. It can be a lot of work. It can be complex, but it is interesting and it is doable. But there is a recent challenge from the LLM world. Is this paper, which I think is very clear about, first of all, using informalization as a way to help auto-formalization by generating synthetic data, formal, informal pairs. But they use actually GPT-4, a language model, to produce this data set, which was a noisy data set itself. Maybe they said 70% more or less acceptable, and then the resulting auto-formalization was maybe 20% acceptable with minimal corrections. And actually, it's these figures that suggested to them that the informalization is much easier because of the higher percentage here. But I think it's easier in a more fundamental way, which has to come from the fact that the formal language is limited and the informal language is unlimited. Anyway, so what's interesting, they have 3 points which are a good way to specify a little research project and also the title of this talk. So they result in natural language content that lacks the inherent diversity and flexibility, rigid and not natural language like. Tools are hard to design and implement, and they differ a lot for different formal languages. And the paper starts with a negation of each of these. So I would like to show that it's possible to have symbolic informalization that has the inherent diversity and flexibility. Tools are feasible to design with proper methods, and they can be shared to multiple languages, both formal and natural languages. So these are the 3 keywords: fluent, productive, multilingual. So let's look at this again. So there is a tradition. Not all of this is actually made for informalization, but rather for CNL, controlled natural language-based formalization. My own work here was from the beginning very much inspired by this paper by Cospoy, Van, and Terry on extracting text from Coq proofs. So to some extent still following the same methodology and sharing the same problems, which is that the main problem is to actually, if you have something formal and complex, if you do it in a too straightforward and simple-minded way, you get something which is even more incomprehensible, even more complex. And you will see examples of this. Yeah, but these are all, I mean, good background for this kind of work, at least showing that it's possible to have more or less nice informal statements for formal languages. So the first generalization that I want to make, at least when compared to some of the systems, is to functions ones that go to many solutions. So in informalization, you may have many solutions or many statements for a given formal statement. And in formalization also, so that you have to admit that there can be ambiguous input that you might then resolve in some other way. And then, of course, that it is partial, essentially. So an extension of a symbolic extension of a pure CNL. So if you put neural alternatives here, so you get similarly something that can give many and maybe many ranked solutions, but they are uncertain. So you can never be quite sure. And this is where this verification feedback comes in. So let's say you want to build a system where the human mathematician or student or whatever wants to communicate with formal mathematics, but see it as a black box that performs verification, but you want to communicate in natural language because you don't want to learn this formalism. This is an artifact that maybe whatever has to learn, although the extra might say that you have to learn it, but I'm still not quite sure, I think. So let's say that you have a symbolic informalization, which gives you something correct and simple here. And when you use it by a reversible grammar, as I'm going to do in the what follows, so then you get also you can get correct answers back. But if you in the interaction enter something that is not in the scope of the grammar, then you get a syntax error or no parse. And then you take this LLM auto-formalization to your help. But as often happens in LLM, so they are not so picky about negation, so it might forget the negation here. And now if the thing on the left is a black box, so how can you know that it is that the auto-formalization has understood you properly? Yes, they use feedback informalization, symbolic. You know that this is exactly the way in which the model has understood you, and then you can judge it without having to look at the formal code at all. And of course, you should imagine that this is something much more complex than these minimal examples here. So that would contribute to this dream of having formal mathematics and natural language, but the communication to most users happening in natural language. So that it is symbolic information is a certificate in the sense of Mailhorn of the system's understanding. Now comes to the positive or constructive contribution to project Informath, informalizing formal mathematics in a way that's multilingual, productive, fluent. And this is a whole picture. So we will analyze some parts of it. You should pay attention to the different arrowheads here because they have gone through a number of iterations, so that I think we want to have something black wherever possible, and also want to have something well, something total to one whenever possible. Otherwise, total to many, and only in limiting cases something partial. And you see that the partial things are everywhere, but they are mostly in the direction from right to left. So this brings us to the first of the buzzwords, multilingual. So you see already here that this is meant to be multilingual. And here is an example, which is one of the simplest examples from the current system. So we have the 3 proof systems, and then we have the it's informalization produced by the Informat system. And this will actually result in all of these three via yet another system which is called deductee, which is, I think, mainly developed 500 meters from here, and which is meant to be an interlingua for the, or a kind of a language that would be able to interpret code in each of the other systems, even more than these three mentioned here. And in this way, we actually can deal with the multiple formal systems. So that was kind of the easiest challenge to meet here. So just a few words about deductee. So it's a logical framework based on the lambda pi calculus modulo, in which many theories and logic can be expressed. Simpler but more powerful than any of these individually. So that is why the arrows in this direction are total. But then there can be proofs in deductee that are not valid proofs in the other systems. So this can to some extent be used for translating between systems, but not. But what we have here has been enough for the purposes that I'm looking at here. So it's a very minimalistic system. So it has dependent types and pi types, lambda abstracts, rewrite rules, and almost no syntactic sugar. So the only syntactic sugar I think there is that you can leave out the variable from a function type when the type is not dependent. So it's similar to, actually, that's why one personal reason why I like it is that it's kind of the types theory as I learned it in the 80s and 90s, and systems looked like in that age. So there was a lot of syntactic sugar. Okay, but then we also have multiple natural languages. And how come this? So this is that we have a common abstract syntax tree for them. This looks more complicated than the deductee code. It's written in the GAP language, grammatical framework. You can also visualize it in a nicer format. So the GF is based on this idea that you have an interlingua or abstract syntax, and then you can translate it through many different languages. And so does everyone here know GF? Because I will give a 2-minute introduction. So it's a grammatical framework based on logical frameworks, mainly the ALF system that was already mentioned here. Adding grammar rules. Started developing it in the 90s at Xerox Research in Grenoble. The mission is to formalize the grammars of the world and make them available for computer applications. But actually it's a bit more, so we also want to have this shared abstract syntax trees. This is a current, almost current status of the GF resource grammar library. So these are the languages that have been addressed to different levels of maturity by the community that has been created around GF. And I will come back to this also while. First, just to see how it looks. So there is this abstract syntax notation, which is very much like a logical framework. Actually, it also has dependent types in this context, gamma, but I will not need them in what follows. And in the concrete syntax, when you have a category, I mean a basic type, then you say how it is linearized, and then each function which forms a syntax tree, you tell how that produces the linearization of the given type. So best to see this from an example, from a kind of a mathematical example. You have two categories, propositions and terms, and you say that they are both linearized into strings. And then you have a function which says that the term is commutative, and surprise, surprise, the linearization function just concatenates is commutative to its argument. And this is the kind of the special case where the linearization types are strings corresponding to what you have in context-free grammars. But then the real strength comes from extending these types to other kinds of types. So you can, for instance, you can have records where you say that the string have a number. So let's say that you have a, you say that addition is commutative. Okay, that's a singular. But if you say that that addition and multiplication of real numbers are commutative, then you have a term which is of a plural number. And this you can add to this grammar without adding anything to the abstract syntax. And then this extends to other languages that may have more of these language-dependent features like gender and mode in French. And then you have to inflect commutative, so that, for instance, you have gains a V when it's a feminine form, so on. And we'll see also how you can do this. But you can still have the same abstract syntax. And all of these linearization rules that were shown here, so they are convertible to parsing rules, so that you can go between abstract syntax and the concrete syntax, abstract syntax trees and concrete syntax strings. And you can combine several concrete syntaxes with the same abstract syntax, so that you have this famous interlingual structure, and as a byproduct you have translation functions between each paired languages. So deductive and GF are used here to make this multilingual. So let's look at the second buzzword, how to make this productive. So surely there's a lot of work if you want to write grammars like this and to take into account everything that you are in a language. And here the key is, as in many other branches of software engineering, is libraries. So this resource grammar library that I showed the map about, so it tries to collect the functions for inflecting words and combining, building syntactic combinations for different languages. And what we need for commutative, for instance, in French, so we need the adjectival inflection. And this is something that is actually a formalization of some grammar rules from some grammar book that everyone has to learn when they learn French. So that as a function of the suffix of the word, then you create different sets of forms. Yeah, this is at least maybe a special case of the full function that we have there, but you can see the point. And so if a mathematician writes commutative, or you get somewhere the translation of commutative as commutative, then you don't need to think about how it is inflected and what forms you need, but you just apply this function mka to the string commutative full inflection. And the other part is to do the same for syntax. So here is the function make CL, make a clause from a noun phrase and an adjective, and you have it in different languages, which takes care of the inflections that are needed here. And you have this kind of functions for most of the syntax that you might need in, for instance, for informalization. And then you can write your grammar in this rather economical way that you have an abstract syntax as before, so this is still the same. And of course, we need something bigger in the full system. You see here how we implement this. So the linearization types now, you don't use strings or records of strings as before, but you just say that this is a clause in the sense of the resource grammar, and this is a noun phrase in the sense of the resource grammar. And then commutative predicate is linearized to X commutative adjective. Okay, and this works for all of the languages that you might need. And then for each language, you have to add a code saying how what is the word for this adjective for commutative. So in English and French, even in Finnish and the other languages, and you can be certain that, or you should be able to be certain that the inflections come out right, whatever forms you need in your application. If you compare this then to this rule, having to write this in a context-freezing grammar, as many CNL applications, at least in the past, did. So in order to take care of all of the grammatically correct combinations, you need quite a lot of different subcategories and their and rules for combining these subcategories, even in the present tense. And in French, you need even more. So this is just a little part of what is actually, I didn't write them, but I generated these from that. So now we have to then combine these two. So deduct is here. So this is our in-house grammar for the parser of deducti that we use. And then we have GF abstract syntax called math4. And you see that this is more or less a complete grammar of deducti, but this is just a part of what we have on the lateral language side. And the reason for this is the following. So we typically have to choose how we convert each deducti definition and each deducti expression, depending on whether the definition is defining a new proposition or a new kind expression or a new individual expression or stating a new theorem with its proof. And these are a simple example of each. So deducti has just expressions and their definitions, and that's the kind of the beauty of it. Do everything with this very minimal syntax. But GF categories have to, here when we are doing informalization, they have to correspond to linguistic categories as different as here noun phrase, common noun, sentence, and text. And these are then built from the resource grammar, and these are the categories we use in this application, the informalization. And here you have examples. So conversion is ultimately driven by type that we give to this identifier. So, for instance, here are some other types that we also need for different kinds of functions. But let's look at a more concrete example. So we say that not in deducti is corresponds to a set expression whose GF function is natural underscore set, whereas EQ is a comparison predicate plus is an operation expression and even is an adjective. And then you can also put GF linearization rules here so that you don't need to actually manually edit the GF grammars. And this is the information that you need for on the, let's so to say, atomic level of the conversion. So if you want to informalize from deductee, then you look up for each identifier in the code, how it is converted to GF, and then proceed from that. If it is not given in the symbol table, then you have some default informalization, which is usually much uglier, but at least you get something. And then you know that if you add an entry to the symbol table, then you will get something nicer. And this symbol table is also partly something that you could automate. So let's say this is a deductive programmer. And it's a new constant Symbolic, which is a function from natural numbers to propositions. And then they just write a comment. So this is the deductive comment syntax. That if GF is a Symbolic number, then you can send this to something that performs lexical rule extraction, where we actually have a good help from Wikidata. Wikidata is a database underlying Wikipedia, which has these identifiers for different concepts, also in mathematics, and then labels for their expressions in different languages. And then from this, you can actually then extract enough of a GF grammar so that you can get the simple type of entries that you need in order to proceed. So what does Symbolic mean? Usually no one knows, but now because some of you have seen this already, so you know. So this is one way to define it in deductee without being all too verbose. This is our informalization, or one of them. Not quite the same yet as we have in Wikipedia, but I think you can get the idea if you read it. So a Symbolic number is a product of three distinct prime numbers. They have some interesting properties. Okay, then these names for or labels for mathematical concepts are usually syntactically complex expressions, and then we need some parser for them in order to put them into a syntax. And here are kind of by some inspection of the data, so I came up with these as being the most prominent syntactic forms in labels for mathematical concepts. And of course you can combine those so that you can get syntax trees for even more complex forms. And this was an experiment actually made last year in the Bonn formal mathematics event, with where I got over 5,000 concepts from some colleagues that had wiki data labels, and then this was the size of the lexicon that was extracted from it. But so far, just as a kind of a library of linearizations, because we don't yet have the formal definitions of all of these concepts. But this was to show that this combination can be made productive. So you use the RGL and GF, and you need to not write so many rules, and even less rules if you can use some lexicon and grammar extraction. So how to make this fluent? And this was, I think this is the most difficult and the most open-ended challenge, because whatever you produce, then someone comes with something which is even more fluent or even more idiom. And, well, then we of course take it as a challenge to add it if we can. One inspiration is Mohan Ganesalingam's The Language of Mathematics, where he starts with an analysis of mathematical language and shows how complex and rich it is. And we want to kind of implement that kind of a view of the language of mathematics in the end. And this is how we do it. So we have this math core, which is very much in one-to-one correspondence with deductee. And then we have a full Informath grammar, where we generate many synonyms of a given math core expression, which are backed up by semantics, so that we can always convert this extended syntax back to math core, so that we can also use it for symbolic formalization. So here is an example. I think it's the same as before, but you have a deductee proposition, and then you have this math core expression, which is basically has an syntax tree node for each node in the syntax tree of deductee. And even for such a simple thing, so it becomes quite boring and difficult to read. So there are some tricks that you can add here. MLG, natural language generation tricks. One is that you can, whenever standard mathematical notation allows it, so you can actually formalize some parts again. So you use kind of normal mathematical symbolism instead of verbose expressions. Then there is aggregation, where instead of saying A is odd and C is odd, you say just A and C are odd. And this results in something that I think in the first talk about this here in Saclay, I was told that Knut says that you cannot have a comma between two symbolic expressions, that there must be some words, and then this is possible to solve by moving the quantifier after. So maybe this is more important for you, that moving something after, that there is a risk that something becomes ambiguous. Come back to this. So there's no such thing as always choosing something that is the best rule, but you have to find the best combination of this. Here is another very typical thing, which is introducing in situ quantifiers. So where you can even leave out the variable. If there is exactly one occurrence of the variable in the body of the quantification. So you have these different ways to score the quality of an informalization, and this is the one that we currently use. And then you can also get an weights, so that you make some linear combination for these. And what one could dream of is maybe to have some machine learning to learn these weights from some mathematical forms. Now I just think that it's, for someone, for instance, it is very important that you don't have any subsequent dollar signs that put a higher weight to this. Whereas I would say that extra parses meaning ambiguity, so that should have a higher weight. Here are some examples again how these scores look. We need to look at this, but basically you, at least with these default weights, so you already get kind of the nicest expressions rank highest or having the lowest penalty. So I think we can at least approximate fluency by these NLG, natural language generation transformations, and then having GF resource grammar library that supports these, because you have to support different kinds of syntactic structures in order to enable this. Still have some time. Some case studies. So probably many of you know this Reich-Wiedeik's 100 theorems that is used as a benchmark for formal proof systems, and here are some of those. And I would just like to show a demo where I build a document that creates all of the, that takes the so I don't have all of the theorems there yet, because I also have I want to have the deductive definitions for each of the concepts, so sometimes it's not so easy to find them. But anyway, so this is the input to this top 100, and then I run it, so then it makes a ranking list of variations for each of them, and then I get 96 pages of statements for these theorems, and they are, because of the ranking, so they are sorted from the better to the worse. So I think much of this becomes quite readable. Nice already, but
they look very good.
Yeah, so there is a kind of room for improvements, and this is of course then inspired by different.
And you put quantifier, well, you can put quantifiers in the beginning or in the end.
Yeah, so this is one of them. And then I can also do this. French. And maybe you can already spot some errors here, but this is very much a byproduct of using a functor. And this, what's now? Who's the missing period at the end of one of them? Yeah, so it's actually like everyone to welcome to debug these things. Because only the German grammar was made by a native speaker, by Frederick. But I think I could spot some errors there. So so it's this is another one. So we had this mathematical Olympiad problem challenge, and started to look at this in the GF summer school a couple of weeks ago with a mathematician who was actually been involved in organizing the Olympiads. And notice that almost all of the symbolic problems have these 3 dots somewhere. And what is the real rule for 3 dots? So this is an example, and this actually comes from, this is not from the Olympiad problems, but it's a kind of a mini example of how to deal with the 3 dots. So these are generated as variant expressions for, where this is of course the kind of the basic thing. But when you do this, so I think you kind of lose track of what really is meant here. So it becomes like an IQ test where you have to, and then you are in trouble because you can, of course, have many ways, you can find many ways to complete this. And I'm sure that when they put this into a mathematics context, they actually think about when exactly it is ambiguous to parse this, but this is I'm confident in this generalization to sigma symbols, but then when to use
You have also
the 3
only
dots.
if. I claim somewhere only if.
Yeah. So there are these. I think some of this actually comes from Knut's book about mathematics. Okay. Next thing, and next case study here was we also started very recently Nafros the Deaf by Adrian. And so it's designed to be a formalization input for formalization in mathematics. So now we're also working on informalization with Mizar, and I don't know that yet. But I've done something similar previously to the 4-cell language, which is a kind of a predecessor of NumRosh. And I think there are some, I mean, this is not meant to be a competitor or something, but that's a kind of an addition. So the way to do is to extend the informers to parse NumRosh data or some other controlled natural language. And this was actually, syntactically, this was quite simple, although you have to somehow times, depending on the CNL you are working with, so you have to actually admit something which is not completely correct grammatically. But if you know that what functions produce such code, so then it's okay. But then when you parse this, so then you can get the deductive code, and thereby also code in these other proof systems, and then you can obtain paraphrases by these MLG functions, and thereby synthetic training data. And this increases the parsing that would target controlled natural language. And then you could also translate to other informal languages, that is German and French and so on. And there are some issues here. So NumRosh has this undeclared variables and variable types, and then how to get proof objects from proof text. So this is so far only working on the level of statements and definitions. So this is from a file called sets. I'm only showing those parts where which have also deduct the translation. Because then there are some of, especially in this LaTeX notation, that is not yet converted to the deductive file. Okay. Then coming back to other formalization, so there is this generation of synthetic data. That is one task, and we did a case study with the master student this spring, and especially targeting Agda, which didn't have so much code yet, and his results were quite striking. I mean, we were able to improve the different scores quite a lot by using this training data. The evaluation was made by handwritten versions of some of the 100 theorems, so the evaluation was not done by Informas generated data. So Nick Smallbone, you may know, so help us with that. So that was promising, but I don't know quite yet how well this generalizes to everything. And there's another experiment that Josef Urban made in Prague for converting this to for using few shop prompting in the Mistral large language model. Okay, so now we come to conclusions. So we say that formalization can be natural and fluent by extending a CNL towards the full language of mathematics, feasible to develop, shared by different formal and informal languages, and invert to auto-formalization, either natively by reversibility, but partially, or as a backup by fine-tuning large language models and then to provide the The technique is based on well understood compiler-like techniques, which can potentially be made 100% reliable. So if there is anything wrong, so it's about to fix. It can be fast and energy efficient. So actually, it runs on MacBook Air, which has the same weight and the same energy consumption as a human brain, so it's much better than the LLMs need much more energy and much more brain power. Natural extension of formal proof techniques, because it's kind of similar kind of technology. An integral part of a reliable AI system for mathematics and other fields where that could be formalized and thereby informalized. Some future work. So haven't shown informalization of proofs yet because they are too bad, so they are too unreadable. It's a kind of the same situation as Koskoi and the others 30 years ago. But basically the syntax of proofs in deducti that you need for deducti is quite simple. So you need these abstractions and applications, and then applications of named theorems, latent theorems. Then we would like to have a better evaluation criteria for auto-formalization. So the blur score that we used here, as well as edit distance, so they just work on the level of comparing tokens and not the structures. Logical equivalence is too liberal, and so is definitional equality. So let's say that you say that an auto-formalization is correct if you get something that is logically equivalent, then you might think that, well, okay, so everything is auto-formalized to true, then it's logically equivalent. Clearly enough. Then we would like to create APIs, connect with proof systems. So use Inform as a library or a component. So it is not meant to be a kind of a replacement of any existing proof system, but to complement them. Enable natural language interaction and documentation. And as such, it is more powerful than these mix-fix and other similar syntax extensions. So one would say that natural language is the ultimate syntactic sugar that one might like to use in a system like Lean or Go. And then, of course, exploit this multilinguality to generate Wikipedia articles or translate international contest problems.
Very much wonderful work here. Please, questions, comments. We have 20, right? After that, you.
Yeah, I don't.
Please welcome. Yes, welcome.
Yeah, so thank you for the talk. I thought it was super interesting. I was wondering if I want to actually informalize, say, statements from Maplet and Lean, is your system ready for that? Like, can I translate it to Deductly, and how would you deal with, for example, I think in Maplet they have a lot of like custom parsers and like custom syntax. Is that kind of expressible in this framework?
Yeah, so we have actually in-house work on this translating from Lean to Deductly. And how far is that work?
Well, you can do the translation. It may not be well typed in Deductly, but you can
always translate.
You can always do the translation.
Yes. Yeah.
But we don't. We translate like post elaboration, so we don't. The syntax carries over into the Deducty output. So.
Right. Okay.
Yeah. So I can already do it now by pushing a button, but you get something really terrible. And as I think you saw it, and I haven't done much progress about that since then. But the one problem is that let's say the informal that I have done right now are like for basic mathematics, and when you have a quantifier, let's say over natural numbers, so it's just over natural numbers. But if you have the full formalization that comes from Lean, you have these layers of levels of universes and universes and types in universes and conversions between types and universes and so on. And basically you have to strip out all of that. And this you can do with rewrite rules, but you have to write these rewrite rules and be guided by something. So there's some work to do, but I think in principle this should be doable. Yes, it is already, but the results are not yet very good.
Right. Yeah. And the problem with doing it post elaboration is that you just get very long.
Yes.
Yeah. Okay.
And you get a lot of things that you don't want to see at all.
Okay.
So and then if you want to do this, trip back, then you also have to know how you restore this so that you can, that Lean can then.
Right. Okay. That's that.
But so I think this is doable, but it's a kind of work that has to be done.
I'd like to follow up on this. All of the Deducty translations I know are essentially embeddings, which means they have a tremendous blow up and lose structure. So what is the kind of the blow up factor in these translations? I know that Henk Barendrecht introduced this idea of the De Bruijn factor, the blow up between the natural language and the formalization. I suspect that there's a something factor in going first to the Deducty representation, and then maybe another factor, which might be bigger or less than one, that goes to the natural language. And ideally, this should really, the multiplication of these two factors that I'm postulating right now should be equal to the de Bruijn factor. How far are we from that?
Yes, unfortunately, yes, the factor is quite large from lean to deductee, maybe more than 50 times. So part of the problem is that the lean output itself is very highly optimized, like the OLEAN files, like they have a lot of sharing of object pointers and such. But when we do the translation of deductee, we lose all that because deductee is just like plain text. So we repeat a lot of things in the outputs. Yeah, there's also a lot of additional deep encoding stuff, like encoding, and that can also cause it to blow up. So I've been trying to get some kind of explicit sharing to work in the output so that we don't have these redundancies, but it's still a work in progress.
But isn't the factor exponential by design?
Yeah, I guess it's somewhat unavoidable, just because you need to preserve all the information, and then on top of that, you have an encoding. So, yeah, but yeah, so you'd necessarily have some bit of factor lean to deductee in terms of the output size, but see if we can minimize that.
So yeah, my experience is that it get you a long way if you say that this lean function f, you drop the first three arguments in rest, and you do it for, you have a symbol table again saying how many arguments you drop, and then before you are informalizing, and then you get something much cleaner, which is already close to what you wanted to have.
So you probably want to drop all the inferred factor.
Yeah, and then I can also rely on that when I go back, so then I put some meta variables there, which then can be restored. So this kind of twin of deductive, which is lambda pi, can already do much of this. So, but might be the way to go. The other thing that I have done a little bit is to add something more, some conservative extensions to deductive. That's of course a slippery slope, but the one that I have played with is to add let definitions, let expressions, because those are the way to one way to split the long proof into lemmas. So we'll see how.
We'll go back to that. Okay. I'll try tomorrow to about the left expression. Symbolic recursion, you can do it more powerfully. I have already proven that Symbolic recursion operator is algorithmically more than there's a theorem firm.
Yeah, maybe it is, but so far
then, but you have to put them not meta. You have to declare them special.
Yeah, so right now it's a syntactic operation that is then can be eliminated by some solutions.
No, recursion operator cannot be eliminated.
Well, if it is
That is the difference.
let rec, then it's yes.
So you can generalize the left expressions to convertible.
And that's also problem languages.
But compilers use that. Formalization of parts of compilers, how they convert recursive programs into iterative. It's usually a automatic process. Okay, both of you, let's see, you rise first.
When you informalize, sometimes you need to generate a statement that is not a composition of the generation of word corresponding to each predicate. For instance, the diagonals of quadrilateral intersecting their midpoints. Can you deal with this kind of construction that are not local GA?
Yeah, no, I think this is actually the way these are implemented. So they are not. There's something that we call almost compositional operators. So they can. They are recursive functions on syntax trees, but they. Okay, so it's actually the code for that is not shown here, but it's. I think it's the whole point that you need to do something which is not compositional, like GF is compositional, which is by design. But here, so it is basically right now pipeline of different like compiler optimizer passes, which are defined separately. So one of them is to take out some parentheses that are used to force a certain scoping. And then you define this for all syntax trees, but you only have cases for those constructors where it matters, and everything else applies this compositionally to all subterms. So that's the kind of technique that we are using. It was developed for compiler passes in Haskell.
I would like to look into this a little bit more. You're essentially showing us, if I understand correctly, rewrite rules for abstract syntax trees written by hand in Haskell.
Yes.
Okay. And you're collecting those and trying to simplify.
Yeah. Yes.
We've been doing something very similar.
Yes.
And we're trying to collect those because I think many of those are relatively universal. And it seems to me that the examples we've seen are almost all, I would say, canonical or foundational rewrite rules. If you think about where they sit in the hierarchy of the man, you're kind of applying simplification rules only for very simple stuff that you can assume your reader will actually understand, rather than doing something with plurisubharmonic. We do introducing pairs, removing pairs, and then dealing with set membership and moving things out and inside of sets via comprehension and so on. That is at least the intuition we have. And I was wondering whether you have similar intuitions or whether you haven't really looked at that much.
So the intuition is maybe similar, but it's so. What I would love to see is the following. So here I have the opposite direction. It's from by eliminating these extensions and the semantic functions, which right now only belongs or depends on one thing, which is that you may need to introduce variables when you have eliminated. And then it just goes through the different constructs which are not in the math core fragment, but on the Informalization fragment, and then eliminates them so that we get everything back to the math core. And this is essentially an inverse of the, but this is a many to one. So semantics is a kind of a many to one. It's a normalizing operation, whereas the NLG is one to many, and the ultimate thing to do this, I think, would be to have one definition of both, so that you just have let's say the semantics, and then you would do some kind of a saturating search of from the of the semantic definitions to apply them backwards. But, so someone who knows more about rewriting, take this as a challenge. But,
How about the still alive?
yes.
Theoretically, I think I know that.
So, but anyway, so here is.
But it's only maybe it's just hallucination.
Here is actually the NUPROS extensions that I also wanted to get rid of. So these are the.
Are those mostly infrastructure to remove deep embeddings, or are those the rewritings we all do when we write down a definition? At least when I write down something for my slide, I find myself kind of reworking a definition 3 times or so to kind of make it more compact or more succinct or more aggregated or those kind of things. Seems to that is kind of that feels different from kind of these undoing artifact stuff.
Yeah, so it's but certainly so this NLG direction is undoing artifacts, and this is restoring the artifacts, and then undoing the artifacts. So I think the best we can do to select among them is to somehow rank them. First, I try to kind of see that the more deterministically see what rules are the best things to apply, but this looks like more the things that you can just guess, you don't know. So then it's better to have some more systematic way of guessing. And then I resulted in these scores, score-based ranking, which would even be maybe learned.
Yeah.
The simplest case is some kind of linear regression. Yes.
You mentioned that there's currently.
Yes.
You mentioned there's currently bugs in the system, so there's mistakes in the output. I was wondering how severe those mistakes are. Like, is it mostly typos and grammar, or does it actually affect the content of the mathematical statement?
That's a good question. So try to be careful about that, but there can be bugs on different levels. So when I'm using these libraries, so the libraries can have bugs, which is of course there are less and less bugs for languages that are libraries are used more. And then the other source of things is that since most of these languages are generated by this having essentially the same syntactic structure, so you don't have they are in some sense they follow the ways in which things are expressed in English, although they use the correct grammar of the different languages, but they don't necessarily follow the conventions for mathematical writing in those languages. And there I think it should be fixed by some native speaker, mathematical speaker inspection. The most serious bugs would be ones that, for instance, lose information. And I think, for instance, this transformation, so maybe it should come with a serious warning that I might not want to use.
So, continuation of the topic.
It's directly to this. What you would really want to do
Yes.
is to have kind of a link semantic link on the dot 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 that essentially lets you hover on it and show you the first version.
Yeah, that would be
And
quite
then
easy.
that would not lose any information, and that would be extremely helpful. But it would be make for, that's what we could do if we, instead of generating PDF, generated MathML or whatever.
Yeah, no, I think that's quite an not a difficult thing.
No, it's not.
to do. So because it's
But
already
we should.
Yeah, no, that's a very good idea.
But well, we're on the slide. What about we don't know the first, and the rule there is much more complicated, more mathematical sequences.
We call that AI hard.
Then
Or
you
AI
know.
complete, I hope.
So then you actually don't know what's behind the dot dot stuff.
Of course.
Yes.
But
So,
humans can do it.
Yeah, just to guess the formula. So welcome.
Thank you for the talk. I wanted to know what was found in the experiment, the synthetic data slide where the master's thesis experiment. There was a. So what did you find out? Like what was the finding of that experiment?
Yeah, so let's go. So we made many experiments because first of all we had a lot of data. So we had a lot of, for instance, we started, I think, very much with deductive data that was obtained from Matita. That was the first thing that I got. We also had the data from this textbook that Shashank had been working on, mathematical proofs or something. That was small data, and then we had the big data. And then we got the baseline was this when model, and then it was trained with, in some cases, hundreds of thousands of pairs in this Matita case. And then we tried to take a part of that as a test corpus and a part of that as a training corpus. And the results were kind of dramatic. So with the baseline, without fine-tuning, we got very low scores. And with the fine-tuning, we got scores close to 100, which showed that this was not a good experiment because the test data was generated, even though it was disjoint from training data, it was generated by the same algorithm. So it was as synthetic as that. So that was not a good, but at least what it showed was that the LLM was quite good at learning syntax. So, yeah. But then we did this other thing with the 27. Well, there were many more variants of these 100 theorems, and then we. So this is actually not quite accurate for the last experiment, because in the last experiment we didn't take the statements of these theorems, but only their definitions of this concept. So we defined what is a square root, and we defined what is a vector addition, things like that. And then we tested with the statements of the theorems. So, and that was kind of an interesting from the AI perspective, is that we train the system with the definitions and test it with the understanding with the statements, because that's closer to how humans learn. So we learn the definitions by reading the definitions, and then when we see a theorem statement that uses those concepts, then we can understand it just having seen the definitions and knowing something about the syntax of the language in general. And this was even then, so we got a rather nice improvement of the scores. And then one thing that we learned, and I'm not an expert at this, but it seems that one epoch, so that means one round of training with the same data, was kind of in some sense much better than running 3 epochs, because it's some overfitting after that. Try to understand this better, but I hope we learned that if we can synthesize data that is not as much data as possible, but focused data that has the variations that we need, then we can kind of get quite a cheap way of training something, and which is then much better in auto formalization. So yeah, a bit vague answer, but this is how I would like to interpret the results. And we were quite happy about the results anyway, although
welcome. Thank you for your lecture. It was very, very interesting. I would like to maybe make a comment and ask a question about mathematical Olympian problems.
yes.
You showed us example from algebra, and I would like to ask: Did you work with all the areas that are covered in mathematical Olympiads? Because there are 4 areas, and you started with algebraics.
Yeah. So maybe I should have said it more clearly, but we just started to look at the problems, and this is not an actual problem from there. I have some slides with,
Yeah, I know.
or some, but this was just the first observation we made, that it is very much based on expressions with 3 dots. So we went,
The most common term, let's
Yes.
say, in that type of problems.
yeah. So and then so this happened we have this GF summer school a couple of weeks ago, and there was a mathematician from Galway, Emil Schoenberg, and he would like to work on this. So we didn't do very much yet, but I think the plan was that we would start by looking at these algebra problems, which don't have all of this Agatha and Wolf and Alice and real world things, but just concentrate on the mathematical concepts and look at if we can formalize those problems and then informalize them into a readable form, and then automatically translate them and things like this. But starting from those, so that's yeah. And this was just the first step, is to know this, is to analyze what kind of language and what kind of notations they use.
Yes, because at my faculty of mathematics in Serbia,
Yes.
we teach course that for maybe 3 years we actually use mathematical Olympians problems and solutions for students' projects.
Okay.
So we have quite large base of the problems and solutions already formalized in Isabel.
Aha,
And
yeah.
students were free to choose which area will they
Yes.
use, and the majority of students actually chose the algebra.
Yeah.
So, let's say my experience is that students decided that this is the most, please don't be mad, but that this is the most easiest area to formalize
Yes.
between those 4, because the other one is like a number theory where you really need to know a lot more mathematics in order to formalize. Then combinatorics, which you cannot even begin to comprehend the formalization of the problem. You can easily write the problem and you can easily understand it. But in order to formalize it, it is so complicated even for an experienced mathematician.
Yeah.
And geometry is area on its own that it cannot be mixed with, I think, at all with this. But algebra seems like maybe relatively straightforward. I think out of all the four areas, that it has let's say complicated terms, but there are few of those
Yes.
terms. They are not. I think that there are not too many.
You know, I think it's a kind of a feasible
Yes,
case study.
it sounds very interesting.
Yeah. And I hope we can soon say something more about it, but I'm not working on it myself, so it's which is there is someone who.
More questions? Casimira, you wanted more questions and comments? Otherwise, Casimira, welcome.
Okay, I was wondering, the example that you showed are statements of theorems. What about the proof? I guess the proof is also a lambda term. But when you generate natural language, you might want to use other conceptions like since n is prime, we know that something like this may be useful.
You know, I think this is kind of belongs to future work that we want to. And one key to this is actually to split the proof into lemmas so that we can then use the names of the lemma. Like saying by this lemma, we can prove that. And by this lemma applied to this, whereas this corresponds to assume blah blah blah, and then you have a proof. And so I think one could get adding let expressions to this. One could get some distance.
I jump immediately into this lemma. It will be very good and not with let expression, but with recursion operator. And lemmas, they will be stated into with parameters that are not pure variables, but special recursion variables. And then one can refer many times to lemma 150 and instantiate the variables, the special recursion variables from the lemma into particular cases for the proof of one or another theorem.
Yeah, the first step is to identify if they are not there, and then that's something that can be done by common sub-expression eliminations to start. But it's a kind of also.
I have idea, but I don't know how.
You can take this and
Let's
try.
go.
So you can get this from here and start hacking.
Some more questions or comments? Otherwise, welcome as a speaker. No, this is
Yeah, let's have a break.
okay. If you let me, I'll stay here probably for the whole week, non-stop. So then we have a break. But thank you for telling me, Michael. Thank you for reminding me. Oh, okay, stop that.
Happy.